Okay, thanks. Especially to the conveners. This has been a really, really interesting couple of days, and I've really enjoyed it. So today I'm going to be talking about joint seismic, geodetic, and oceanographic experiments for improved climate change, sea level rise, and tectonic and solid Earth constraints. You might guess from the order of these things what kind of scientist I am. But this all started as over conversations with Nicholas Harmon and Elena Fricker-Williams. We were friends who didn't really plan to work together, and then realized that we had actually a lot of really meaningful overlap, and also continued this with a bunch of other really great collaborators. Yeah. Okay. Thanks. Okay. So I'm going to start with why this is important. And I know everybody in this room probably thinks that either studying the ocean or the solid Earth, maybe both, are really important. But I want to remind you also that the solid Earth and the oceans are intricately linked. Water, enables our habitability of the planet, but the water also is likely involved in allowing plate tectonics to occur, which is also thought to be really important for planetary habitability. However, these tectonic motions also cause a large amount of really dangerous hazards, things like earthquakes, tsunamis, and volcanic eruptions. And so we'd like to understand those tectonic plate motions and the definition of the plate for its importance in terms of hazard, and also just general understanding of Earth's evolution, big questions about the formation of the continents, and also the driving forces of plate tectonics. The solid Earth is also very important, as we've heard these last few days, for our understanding of climate and sea level. Okay, so just some details. We know that sea level is rising at about 3.2 millimeters per year. The AMOC, or the Atlantic Meridional Overturning Circulation, is slowing at about 0.5 spheres per year, or 3%. And this has big implications for things like islands, ecosystems, and their effects on humans, climate, and it's really important for coastal regions. We're also really interested in helping people who have lived near places like earthquakes and volcanoes. And I think everybody here would disagree that everyone is affected. But there's other things that we need to think about, and that's things like the sea level rise is not necessarily uniform, and there are discrepancies in terms of how much the currents are changing depending on where you look on these mooring lines on Earth. So we probably all agree that measurements from the seafloor are an obvious place to start doing a better job, and that these are affected by solid Earth and oceanographic signals. However, solid Earth scientists and oceanographers do not typically interact in any meaningful way, except for maybe us. We're trying. Okay, so that's probably because the time and also the length scales of these phenomena can be quite different, right? Typically, we think of tectonic plates as moving in large distances and over millions of years, geologic timescales, whereas we typically study oceanographic effects at smaller scales and also shorter timeframes. But we've heard a lot about this today. Things like earthquakes, slow slip events, and volcanic motions do overlap with oceanographic signals, and so it's in our best interest to do a better job pulling these apart. Okay, so we have heard a lot about how the Atlantic is really important to oceanographers, and also the Pacific for some. Okay, 40% of the U.S. Population lives within a coastal county. That's 127 million people. These ocean currents are slowing, and this modulates the climate of the surrounding continents. So that's a really big deal. And the oceanographic community has recognized this for some time. It's been working for decades now at looking at these currents, right? So we have here the OSNAP current in the north, the oceanographic mooring line in the north to look at the currents. There's the rapid MOCA line near the Bahamas. And then we have the MOVE line, which is near the Lesser Antilles, and the Samba line in the south. And the currents are drawn by the red and blue, which Matthias and Eleanor talked a lot about this morning. Okay. However, these oceanographic current estimates typically do not account for tectonic motions. And so we know that they exist. We know, for instance, that glacial isostatic rebound is really important, particularly in polar regions. We know that things like volcanic inflations can be really important, and also places where the plate is subducting, such as in the Lesser Antilles, can also have really important vertical motions. Sea level estimates also require some amount of correction for these motions, and they do some things. Like, for instance, one way that they look at this is they kind of take isostatic rebound from geodetic measurements on the land and extrapolate these into the ocean. It's not the best assumption because the oceanic plates actually behave quite differently than the continental plates in general. They're thinner, and so these other, and the other things that we have these tectonic motions, which are not really accounted for in those estimates. And then there's just this whole idea that we've talked about this a lot, but there's very, very little geodetic data in general, right? So that's just the great unknown factor that we'd like to do a better job with. Okay. So I know a lot of solid earth scientists are very interested in the Pacific, and I love the Pacific. But here's my kind of story about the Atlantic. So traditionally, I was the kind of scientist who really liked understanding the tectonic plate and its definition. We have this classic understanding that the plate should get thicker and also colder, and that should be reflected in seismic waves with age. And it does do this if you average in the Pacific. And that's great. It means that temperature is defining the tectonic plate to first order. However, this is not true for individual transects. And in addition, we had this large experiment in the Atlantic. This is in the equatorial Atlantic. We had 39 ocean bottom seismometers that were broadband and 39 magnetotelluric instruments. There was also an active source component. Here in the equatorial and Atlantic, we found things that were much different than predicted by simple thermal models. We found evidence for punctuated anomalies several hundred kilometers off axis, indicative of upwelling and likely a small amount of melt. We also found evidence for downwellings, and we found evidence for a small amount of partial melt in a channel beneath the plate, which likely affects the definition of the plate and aids plate tectonics. So there's so much that we need to know in terms of imaging the tectonic plate in general. And so this is why I think that the Atlantic mantle is also interesting to solid earth scientists. Okay, so as I said, seismologists in general would like to know more about mantle dynamics. So we want this and all of these interesting interactions that are likely occurring. To get this, we really need to do a better job of ocean pressure. And so we need this. We need all of these really nice measurements from oceanographic moorings. Also, precise bottom pressure would be really useful because, as we've heard, the oceans are affected by a wide variety of phenomena. These include additional mass from glaciers and terrestrial release, density changes from temperature and salinity, and then also the tectonic motions from things like normal faulting or volcanic inflation. Okay, so we deployed two Sonardyne AZA fetch pressure sensors in February this year. This is by the Rapid moorings. You can see the instrument here. We have a recovery line, recovery beacons that we added to the instrument, and also an acoustic release. They're deployed in water depths of 4,800 and also 3,800 meters depth. These are next to oceanographic tall moorings that are part of the rapid array. And this is the control site. We don't expect actually large tectonic motions in this area. So we'd like to just see that they're doing a good job. So we have 1 hour sampling, a digiports pressure self-calibration. We also are measuring inclination and a PI's inverted echo sounder and temperature. They calibrate every 2 days and gradually increase to 28 days. And we plan to deploy for 4 to 5 years, assuming that the data we recover is good. This is also in collaboration with Eleanor Fricker-Williams and Nick Harmon. Okay, so I do have a tiny bit of data. We have data from one of the sensors for 1 day and data from the other sensor for 1 week. This is just the raw data. Over here, we have the calibration for the one instrument and then the second one. And you can see that they are different. And so it's doing something that's good, okay? Okay, so let's go on to looking at the tides. Here we have the data still with the tides from the single day and then from the whole week. Below, we have the records after taking out the tides. And you can see on the bottom right, you can see that there's a relatively flat in the signal where the tides have not been subtracted. But when we detide, we seem to get a little bit of a trend in the data. We compared this trend, so that's the black line still, of the tide corrected data to the barometric pressure from the ship in the colored lines. And you can see that there's seems to be a vague kind of difference in the trend, one going up and one going down. This is what we expect for the inverse barometric effect. In other words, when there's lower pressure, that's kind of where the water wants to go. So it seems like it's working, and that's good. Stay tuned for hopefully some beautiful data and some slightly kind of deeper interpretations in the future. Okay, we have plans to also deploy 2 AZA Sonardyne fetch pressure gauges in 2025 near the MOVE moorings. And Matthias talked a little bit about this before. This is in collaboration with Nick Harmon, Uwe Send, Matthias Langhorst, Brandon Crowell, Glenn Sasakawa, and Mark Zumberg. We will deploy these just off of Guadalupe and then further out towards the Mid-Atlantic ridge. We're also planning to deploy GNSS-A stations and some strong motion ocean bottom seismometers to look at the seismic signals. Okay, so this region is interesting because there is a lot of moment that's released seismically. You can see that here, these are all earthquakes. And then you can see that these are OBS that will be designed to go around, the mooring and the APG, and just to zoom in on the sites. And then you can see that these earthquakes that we expect, some near the surface, which we're mostly sensitive to, and some deeper ones going down with the slab. But we may also see evidence for slow slip or aseismic slip. We just don't know yet. Oh, I want to say this. So basically, I've had some conversations with oceanographers who didn't know what a what a beach ball is. And so I was just going to tell you what a beach ball is, because it's always nice to look at a video of an earthquake, right? Anyways, so okay. So this is like kind of where the beach balls come from. It just describes the sense of motion on a fault. Black is always compressional and white is dilatational. So there you go. So we've got pressure and also so pressure in the black areas and then dilatation on the white areas, and that's kind of how we describe motion on a fault. Here, and then this happens in the earth kind of like this for a thrust fault when the plates are moving together like in a subduction zone, and you get kind of a focal mechanism on the side like that, and then also at the surface it would look something like that. Yeah, so that's where we get those beach balls. They mean tectonic motion is probably happening. Okay, let's see. Yeah, okay. And then this is just what a normal fault looks like, or when the plates are moving away from each other on the fault. Okay, so I'm looking at side view and then looking at the surface. Excellent. Okay. Okay, great. Okay, so here are just the focal mechanisms from our study region. This is Guadeloupe, where I also actually had a big seismic experiment. So we have some great idea of what the seismicity is looking like by Guadeloupe and in the Lesser Antilles, because we just had this experiment. And you can see here that anything that's not kind of this green strike slip kind of earthquake is showing you evidence for vertical motions. And here the plate is moving at about 2 centimeters per year. So, it's not all going to be perfectly vertical, but this is getting to the range where it's actually kind of something that you need to pay attention to. Okay, so in conclusion, the solid Earth and the oceans are intricately linked. Their measurements from the seafloor are critical for our understanding of the solid Earth and plate tectonics, hazard, oceanographic current estimates, sea level, and climate change. The Atlantic currents are particularly important, not partially, definitely particularly, for sea level and climate and solid Earth. The Atlantic is important for solid Earth studies as well. Yeah, the scientists must study the solid Earth and the oceans together. Our preliminary AZA bottom pressure data from the rapid array looks really good, so stay tuned for more. And I just want to say that I see this as a much bigger initiative for joint oceanographic and solid Earth studies. We need to do a lot more of this. This is, basically in situ seismic imaging of the seafloor is the final frontier of seismic imaging. We have a lot of land data, and it's the same thing for geodesy. And so, we need to do it, and we need to do it well with oceanographers. The only thing I want to point out, and not to end on a negative note, this is a positive note. It's really hard to get interdisciplinary funding for things that are fundamentally interdisciplinary, right? Because it's really hard for reviewers to totally grasp the other side of the story, and there's a lot of negativity. So I think we need to talk as a community about how we can, convince some funding body that sea level and climate and solid Earth are really important, and that we need to find a way to work together, not kind of separately in our silos. Okay, thanks.